Good morning, everybody. Thank you, Radley. Thank you, Austin. Do you have any question before I start talking about new subject? Thank you, Emma. Okay, I don't see any question. So let me go to my whiteboard and remind you that so far, when it comes to functions, uh, for okay, let me make this sharper. It's not sharp enough. Okay. The test is next Wednesday. I will let you know on next Monday. Uh, but pretty much it will be uh, whatever we left for test number 2 up to whatever I teach this week and Monday. Anyways, we will the main topic for the time being in chapter 17 is mapping. I talked about um, linear functions. One more try, make it, let's see if I can make it sharper. I don't know why. Okay, so we talked about 1 over z, the reciprocal function, and also z square. And last Wednesday, I talked about Joukowski's airfoil, which is z plus 1 over z. Now, today, I want to talk about this linear fractional transformation. It's also called Mobius function. So it is a now whenever we deal with this, we have this condition that A times D minus B times C be non-zero. And the reason for this condition is that if A D minus BC be zero, this is what happens. You take BC to the other side, and if you divide by C and D, you will have A over C is the same as B over D. Now, here is A over C is the same as B over D. If we call it K, then from these equations, you can find A is K times C and B is K times D. And if you replace it in that WZ, or this linear fractional transformation, this is what you get. So if you factor K, numerator will be CZ plus D, and CZ plus D cancels out. You will get a constant. So in order to avoid getting a constant, we always impose this condition that whenever we deal with this function, A times D minus B times C be non-zero. Okay. All right. Now, I'd like to have some observation about this function. Of course, if I put the coefficients in a matrix, then A times D minus B times C is determinant of this matrix. So actually, we are saying that determinant of this matrix be non-zero, and determinant of the matrix be non-zero, that implies that the matrix has inverse, and here is the inverse of the matrix. So, just a little observation. Now, there are a lot of other observations that I will talk about these observations one at a time. So here is the linear transformation or Mobius. The first observation would be, all right, let's see. If we take derivative, what happens? Now, of course, you use quotient rule, and the condition AD minus BC being non-zero. This implies that this derivative can never be zero, right? Derivative not zero. Remember last time when I talked about conformal mappings, a function is conformal at certain point if and only if derivative be non-zero. That means this linear transformation, linear fractional transformation, is a conformal map. That is our first observation. Okay. Now, the next observation is, what about inverse of this function? If you call this one W, in college algebra, you learned how to find inverse of this function. You simply multiply out, right? Cross multiplication, and solve this one for Z. So bring this AZ here and DW the other side. And if you factor Z and solve it for Z, this is what you get. So this again is a linear transformation, right? But this time the variable is W. Anyways, good news. Second observation, if you're working with a Mobius function, it has inverse, and its inverse, also a Mobius function, is a linear fractional transformation, right? Any questions so far? I will have several other observations and put those observations together and find beautiful properties of the linear fractional transformation. Here is observation number 3. What happens if we have two linear fractional transformation and we compose them? Composition. Okay, here is what I mean. So here's f of z, is constant a1, b1, and c1, c d1. And here is g of c. Both of them linear fractional transformation. Let's form f of g of z. So in f of z here, you replace z by g of z. And if you do that, this is what happens. This is g of z. A1 g of z plus b1, okay? C1 g of z plus d1. Now, let's simplify this. Just multiply top and bottom by this denominator C2z plus D2, okay? And after simplification, again, you're getting a linear fractional transformation, right? So, observation number 3 is that if we compose two linear fractional transformation, the result again is going to be a linear fractional transformation, right? Any comment, question before I go to observation number 4? Right. I will give you a minute or so for those of you who are taking notes. Make sure that you're not missing any of these composition manipulation. Okay. All right. Let's go to observation number 4. Before talking about observation number 4, here is a definition. Here is a terminology we use whenever we are dealing with a function. We say x0 is a fixed point. Fixed point means if you plug it in, it will produce the same thing. All right. And of course, one of the problems that you are going to see in this section, there is a function, and you will be asked, okay, go ahead and find the fixed points of this function. So the fixed point has the property that if you plug it in, the output will be itself. That's called fixed point. Now, when it comes to Mobius function, this function can at most have 2 fixed points, cannot have more than 2 fixed points, okay? Cannot have more than 2 points. And here is the reason. So let's find the fixed point. How do we find the fixed point? We let this to be equal to z, the input, all right? And see what happens. Okay, here. And by the way, this is the technique in finding z fixed points. So here's the function. We want to be equal to z. So after you multiply, cross multiplication, so you will get cz squared plus dz equals az plus b, all right? Bring everything to one side, and you will have a quadratic equation. And we already know a quadratic equation cannot have more than 2 solutions, all right? So that is why. Here is a good justification for why this function cannot have more than two, at most two fixed points. Okay. Now I'm going to put all these four observations together, and to prove, in order to prove this result, that whenever you have a linear fractional transformation, this linear fractional transformation is completely and uniquely determined by 3 points and the images of these 3 points. Oh, by the way, these 3 points gotta be distinct, because remember observation number 1, derivative is 0, right? Derivative cannot be 0. So the function is, in a way, 1-to-1. All right. Here is the proof, a little justification for this fact that 3 points, Z1, Z2, Z3, and their images, W1, W2, W3, will uniquely determine that linear fractional transformation, right? And here's why. Suppose we have, this is called proof by contradiction. Suppose we have two Mobius functions with these properties. Okay, one of them let's call W, the other one let's call S. Let's say we have S of S that satisfies the same thing. S of Z1 is W1, S of Z2 W2, and S of Z3 W3. So by one of the observation, I noticed that the inverse of any Mobius function is again a Mobius function, right? What does this inverse do? The inverse will go the other way around. So S inverse of W1 will be Z1, and S inverse of W2 will be Z2, and so on. Now, if we compose this to S inverse and W, remember the observation number 3 was the composition of two linear transformation again will be a linear transformation, the linear fractional transformation. But let's see what is the behavior of this function on those 3 inputs. Look, if I plug Z1, W of Z1 is W1, but S inverse of W1 will be Z1. So S inverse OW, which is a linear fractional transformation, here Z1 will be a fixed point for this function. Z2 also will be a fixed point. And Z3 will be also a fixed point. And this is contradiction because a linear fractional transformation cannot have three fixed points. That's observation number 4. All right, cannot have these 3 fixed points. So this contradiction was, we came to this contradiction because we assumed that there are 2 of them. There are 2 linear fractional transformation. So that proves this beautiful fact As soon as you have 3 points and the images of those 3 points, you can determine that linear fractional transformation. All right, I will give you a minute or so for those of you who are taking notes, and after this, I will let you know how we apply this beautiful fact. And the beautiful fact being the theorem that 3 points and images of those 3 points will uniquely determine that linear fractional transformation. Any questions so far? Observation number 3. Observation number 3 was composition of two linear transformation. You have two linear transformation here, F and G. Composition again is going to give you here at the end another linear fractional transformation. Okay, are you done, Bradley, now? Thank you. Okay. Any comment, question about this proof of theorem? Are you done with that one so that I can go and give you an example? Remember, the fact is this. Any linear fractional transformation is completely and uniquely, of course, determined by 3 inputs and their images, all right? Now, here is an example. So, given 3 points, inputs, and their images, we should be able to construct that linear fractional transformation. Now, here is a formula for that one. W1, W2, W3 are the images. Z1, Z2, Z3 are, of course, the inputs. Okay. You plug the inputs Z1, Z2, Z3 and their images W1, W2, W3 in this formula. You solve it for W, and that is the linear fractional transformation. Now, example. We would like to find a Mobius function that sends 1 to -1, I to 0, -1 to 1. That's what I meant by the inputs to these outputs. So Z1, Z2, Z3. Here is W1, W2, W3. Plug it in here. This is what we get after plugging in. Okay. Of course, -1 divided by this is just -1. And we can simplify this. And then this is an equation in W and Z, but we would like to solve it for W. All right, we will solve it for W. And here are I already did this for you. And after you go through this solution, this is what you receive, all right? So that formula, this is just an application for that formula. And the formula is in your book as well. I will talk about that. I will talk about what happens if one of the inputs is infinity. For the time being, I just have 3 inputs and 3 outputs. Usually, if one of them is infinity, you will, for example, if Z1 is infinity, so you will get rid of this divided by this if Z1 is infinity, all right? Or if W2 is infinity, you will get rid of this fraction, the infinity over infinity, all right? You will get rid of this. So, but one thing that I would like to emphasize here is you don't have to just follow this formula or memorize this formula. A lot of times it's extremely straightforward and easy. For example, this problem that we just did here. What this problem is asking is, since these are the inputs and these are the outputs. So we want Wi be 0. Certainly, numerator got to be 0 if we want Wi to 0. So numerator is C minus I, all right? Denominator, CZ plus D, okay. So I used this information. I used this part. How about using these two? W1 -1, W -1, 1. If you use this one, we already, of course, had. So if you plug 1 here, you want the output be -1. So 1 minus I, C plus D should be -1, which is this equation. And if you use the other one, plug -1, we want to get 1. You get this equation, which is 2 equations with 2 unknowns, all right? So it's not that bad. Just if you add them, you get 2D, and here -2D is -1. And as soon as you have D -1, you can find C, which is I. All right, we found DNC. Plug it in here. Done. Okay. So the point of this demonstration is that although that formula works fine and theoretically is what we expect, but in practice, you don't have to use that formula, right? You don't have to use that formula. Any shortcut that you can come up with would be perfectly fine. Any comment, any question? Okay, well, so also theoretically, there is a correlation between the collection of all matrices, invertible matrices, and the uh, linear fractional transformation. So we can associate this with this one. Just forget about z's, pluses, and this. So A, B, C, D, this matrix. And the inverse, we just found out, here is the inverse, all right? Inverse of that matrix. And we can have a one-to-one association between the set of all linear fractional transformation and the set of all 2 by 2 invertible matrices. So that's an extra information I just wanted to give you. But here's another fact. As a mapping, what does a linear fractional transformation do? Well, one beautiful fact is this. Any linear fractional transformation maps lines and circles to lines and circles, all right? Okay, here I should emphasize that although I say it maps lines and circles to lines and circles, but that doesn't mean a line necessarily goes to a line. A line can go to a circle. And a circle can go to a line, all right? So the totality of lines and circles will be mapped to lines and circles. Let's see why that is the case. Of course, this is a very beautiful fact. As soon as you know this one, and someone asks you to find the image of a straight line, you definitely know that the image of that straight line is going to be either a straight line or a circle. It's not going to be a parabola, for example, or it's not going to be a hyperbola, all right? Here is the reason. If we do a little manipulation here, for example, we can do the long division. We can write this as the constant A over C plus this constant times this fraction. Okay? You can just do a little long division, you will get this. Or now, we know that if we add a constant, of course, adding a constant to a line or a circle, it will make a line and a circle. So, and multiplying by a constant also will do the same thing. If you have the equation of a line and you multiply it by a constant, by a number, the image again is going to be a line. And if you have a circle and you multiply the equation of that circle by a constant, again, you are going to have a circle. All we need to do is to take care of this factor right here. And this is just, in a way, a reciprocal. So it is enough to prove this theorem for the function 1 over z, w equal 1 over z. All right, so by this a little observation, it is enough to prove that theorem for w equal 1 over z, the reciprocal function. All right, well, here is equation of, in general, a circle in xy plane. Could it be equation of a line? Yeah, when a is 0, this term will vanish and you will have a straight line. So in xy plane or z plane, equation of a line or circle definitely is going to be right here. Well, this x squared plus y squared, I'm going to write those in terms of z and conjugate of z. Look, here's conjugate of z, right? If I subtract, I'll get 2iy. If I add them, I'll get 2x. So I will replace x by z plus z bar divided by 2. And I will replace y by z minus z bar over 2i. And I will replace x squared plus y squared by z times its conjugate. This is what I get. So that equation, this equation expressed in terms of z and z bar becomes this equation. Now, let's apply w equal 1 over z, or z will be 1 over w, all right? So, if you replace z by 1 over w, here we will get 1 over w bar, so a over this. This is for z plus z bar. Here's z minus z bar, and here's d. Now, let's multiply the whole thing by w times w conjugate to get rid of these denominators. And if we do this, this is what we get. All right, this is what we get. In UV plane, remember, the image will be in UV plane. W plus W bar over 2 is just U. Here, this is v. And here is u squared plus v squared. Okay? So after applying w equals 1 over z, we get this equation in UV plane. And this equation in UV plane is equation of a circle or a straight line. It will be circle if d is not 0. But if d is 0, you will get a straight line. And that proves that fact that Mobius function sends a straight line to a straight line or a circle. Mobius function sends a circle to either a circle or a straight line, okay? So be careful. You shouldn't say sends a straight line to a straight line. No, a straight line can definitely go to a circle in with this linear fractional transformation. Any questions so far? Any comment? Any question? All right, no question. Good. Let's see if I can give you an example here. So for a linear fractional transformation, for convenience, you see, if the denominator is 0, it will be infinity, and that is when z is negative d over c. And if you take limit as z approaches infinity, you'll get a over c, right? So for convenience, we will include infinity in our arithmetics here. So t of infinity is a over c. T of when denominator is 0, negative d over c is infinity, okay? All right. And here's an example as dealing with infinity. Radley asked about it. This is, of course, one of the examples in which infinity is involved. So I'm going to find a linear fractional transformation that sends 0 to 0, I to 1, infinity to 2. Okay? As soon as you say it sends infinity to 2, look, a over c has to be 2. Oh, we can say, well, look, 2z plus b over z plus d. That will do. All right, just by this particular one will give us one of the parameters, one of those constants. And z equals 0 is going to be 0. So there is no constant. You'll get rid of that, gotta be 0. So in numerator, you have 2z. In denominator, you have z plus d. Okay, right away. Here is just by using this information, t of 0 is 0, t of infinity is 2, you get to this point. You have one more constant to take care of, and that is d. All right, that is D. And we will use this last piece of information. T of I is 1. If you plug I, you're supposed to get 1, all right? So D is I. And here is the answer. Any comment, any question about this example? Sure. Which one, which part did I go fast, Emma? Okay, okay. Yeah, why not? You go ahead and write it down, and then I will re-explain that part. All right, whenever you're done writing, please let me know. Good. Okay, here is the situation. We would like to find a linear transformation that sends 0 to 0, I to 1, infinity to 2. Okay. Well, how can t of 0 be 0? Oh, here, if this is the function, if you replace z by 0, t of 0 will be b over d. B over D gotta be 0, right? How can B over D be 0? The only time that we will get 0 is when B is 0. So that takes care of B. So T of 0, if you plug 0, in order to produce as output, produce 0, B is gotta be 0. Okay? That's one thing. The other piece of information is right here. If you plug infinity, we are supposed to get 2. Well, at t of 0 equals 0 gave me b is 0. Now, talking about t of infinity being 2. T of infinity is A over C. We can do this one at a time, maybe. I'm going to use another piece of paper for you, Emma, to fully explain what's happening here. I should have done that earlier. Okay, here. Let me use another piece of paper here. Okay, good. So starting with T of 0 being 0, that implies B has to be 0, right? So when B is 0, what happens? When B is 0, you will get T of Z becomes AZ divided by CZ plus D. B is already 0. Now I will, these are constants. Definitely A is not going to be 0, right? A is not going to be 0, or C is not going to be 0. That is why maybe I should divide by one of these parameters to make things a little bit easier. So I can write this, if I divide by C, I will get A CZ divide by C, Z plus D over C. Although it looks 3 letters that we need to find, but in fact, it is just 2 of them. You can call this one A, you can call this one D, all right? Why don't we do that? I say AZ divided by Z plus D. All right. So far, I have found that the function that I'm looking for looks like this. Now using T of infinity 2. T of infinity, if you plug infinity here, is A. So this implies that A has to be 2. Good news. So everything is down to the fact that the function we are looking for, we would like to find the function that satisfies applying those 2 conditions. So far, we know that it is 2Z in denominator, Z plus D. Okay. So now the question is, what about D? What about this? Well, for that one, I will use this information that if you plug I, you got to output should be 1. Okay. So if you plug I here, output should be 1. So that means I plus D is 2I, okay? And D is I. Does it make sense now? Wonderful, wonderful. All right, any other comment, any other question? Well, you know what, this covers, pretty much, this covers section 17.2 and 3. Please go ahead and read those two sections. I was going to cover also 17.4, but it might be too much. I will talk about 17.4 next time on Wednesday. All right. Any comment? Any question? All right. If you don't have any question, please go ahead and read this 17.2.3. And if you have time, you can go ahead and read 17.4. All three sections are about Mobius function, and I will completely cover this 17.4 and possibly 17.5 on for Wednesday. Have a good day, everybody. Thank you, Radley.